Welcome to AP Physics 1 practice for rotational motion. So we're getting to about 7 examples here today, all to do with rotational motion ideas. So our first example here, we have a 6 kilogram rock is suspended by a string from one end of a uniform meter stick. What is the mass of the stick if it is balanced by support at the 0.2 meter mark, and that is shown in the diagram here? And what is the force of the fulcrum that it exerts on the stick in order to keep the system in static equilibrium? Alright, so this is going to be in 2 parts. I'm going to break it up into 2 slides so it doesn't get too messy here. The first part, I'm going to work with part A, then the second slide, I'll work with part B. So what does static equilibrium mean as it is said there at the very end of part B? So early on in the year, when you were working with just forces, it meant that all my forces would balance out, or the sum of forces is equal to 0 and the object is not moving. Because you could have sum of forces equal to 0 and an object would still move at a constant velocity. For these situations, it's static equilibrium, it's not moving. What we also need, along with the sum of forces equaling 0, we need the sum of all torques to equal 0. So that's where the balancing act comes in. So in order to actually balance this meter stick and this 6 kilogram rock, we're going to have to do the sum of all torques. So the sum of torques, we're going to write out here, is going to be equal to 0 because I am not moving. So sum of all torque is equal to 0 here. So what do I have here on this meter stick? On my diagram here, I have a 6 kilogram rock that is going to create a torque by a force Fg. You have the fulcrum here, which is my axis of rotation, pushing upwards on this. So we're going to have the torque there. It should be 0 because it is the axis of rotation. It is 0 meters away from that rotating spot. And then when you have a stick like this, or a bar and it has mass, what you're going to do with this is measure it from the center of mass. So that center of mass is creating a torque upon the axis of rotation. So you're going to have at the center of this meter stick, the best I can show here, going downwards, that is Fg on the meter stick. So that is also creating some torque here. So in order to actually balance this all out, basically, since the torque at the axis of rotation is going to be 0, the torque of the meter stick is going to be equal to the torque of the rock. So I'm going to show all 3 torques here, and I'm going to explain which one's going to be positive and which one is going to be negative. So let's show some of the torques. It's just adding up all the torque together. So torque 1 is going to be the torque of our rock here. So the rock, if it were to rotate based on the rock hanging downwards, is going to rotate in a counterclockwise direction. For our sign conventions here, counterclockwise is going to be positive, clockwise is going to be negative. So the torque that the force of gravity of the rock exerts on this meter stick is going to be a positive torque. So that is torque 1. So I'll put this here. Torque 1 is positive. Torque 2 here, again, it doesn't matter if we add this or subtract it. It's going to be 0 for the fulcrum. So we're just going to add torque 2 because it is the axis of rotation, and I'll show that in a second. And finally, we have the force of gravity of the meter stick that is going to rotate the meter stick if it was unbalanced in a clockwise fashion. So this is going to be a negative torque. This is all equal to 0. So a little quick algebra. Send this over to the other side. This will cancel out. And I'm going to be left with torque 1 plus torque 2 equals torque 3. So now I'm going to plug in my equations here. And what is my equation for torque? It is going to be the force that I have on the object, and this one is going to be Fg. R and sine theta, but when you have a object that exerts a force perpendicular to the object, that is going to be an angle then of 90 degrees. if you plug into your calculator sine 90, that is 1. So we're not going to write sine theta here since we know that is going to be 1. For our torque that is exerted by the fulcrum here, this is going to be a force upwards, and our radius is going to be 0 because that is the axis of rotation. And then we have another Fg, and this one is going to be Fg, and this is of the meter stick, times the radius, which is the distance away from the axis of rotation. All right, so we should have here again and again sine theta here. It is a perpendicular force, so sine theta would be sine 90, and it's going to be 1. So we're not going to plug this in here. So we should have here that FGR for the rock is equal to FGR for the meter stick. So we have the mass of the rock, so we can use that here. So what is Fg? Fg is mg, obviously. So let me just write this out a little bit further. So Fg is mg times r, and that is of the rock, is equal to the mass of the meter stick. I'll put a subscript m there, times g times r. So what we're looking for here is the mass of the stick if it is balanced at the 0.2 meter mark. So our axis of rotation again is the fulcrum there. How far is my rock away from that fulcrum? It tells me that is 0.2 meters. So what I have here, I'm going to plug in 6 kilograms for the rock times g, which is the acceleration due to gravity, 9.8 meters per second squared, times the distance from the axis of rotation, which is going to be 0.2 meters. This is then equal to the mass of the meter stick, which we do not know. So we'll put m for the mass of the meter stick. Gravity, again, is 9.8 meters per second squared. Times the distance from the axis of rotation. So if we measure the mass there, or the force of gravity, from the center of mass, and that is what is created in my torque, and we have a meter stick, what is the center of this meter stick? The meter stick, halfway through, a meter is 1 meter, halfway through that is going to be 0.5 meters. So if we are at 0.5 meters here, where we have the center of mass, so this is 0.5 here, the distance from 0.2 to 0.5 should be 0.3 meters. So our distance from the axis of rotation, 0.5, since that's the center, minus 0.2 we already have here, because that's the distance from the rock to the fulcrum. Subtract those two numbers, and the difference between how far away the center of mass is going to be from my fulcrum is going to be 0.3 meters. Alright, so the only thing I should be missing here now is my mass of the meter stick. So let's plug in all our calculations here into the calculator, and we should end up then with our mass of the meter stick. So 6 times 9.8 times 0.2, that is going to give me 11.76, my bad. And that is newtons times meters for a torque. What else do we have here? We have the mass of the meter stick. And then we have 9.8 meters per second times 0.3. And that is going to be 2.94. 2.94, my bad. And the units here should end up being meters squared seconds squared. All right, so when we do all this now, the only thing I'm going to have left here to do is get my mass of the meter stick by itself. So in order to do that, I'm multiplying it by this value here, 2.94 meters squared seconds squared. I'm going to divide this out from both sides since that is the opposite of multiplication. and I'm going to end up with my value for the mass of the meter stick. So this will end up canceling out. I have 11.76 newtons times meters here, and I will end up with my mass of the meter stick. And when I plug this into the calculator, 11.76 newtons times meters over 2.94 meters squared seconds squared, and I should end up with a mass of the meter stick as 4 kilograms. That is going to be my final answer. So let's move in now to part B, which is finding the force the fulcrum exerts up on the meter stick. All right, so now in part B. So in part A, we figured out the sum of torques, what torques would be present in order to keep me in static equilibrium. Now we need to figure out the forces that are going to be present to keep me in static equilibrium. So this is just a sum of forces question going back all the way to dynamics. So let's see the forces that we have present here. We kind of figured that out already in the first part of the question. We have a force of gravity going downwards from the 6 kilogram rock. We have a force of gravity going downwards of the meter stick, and we should have a force being pushed upwards from the fulcrum here. So we'll call this just F. All right, so this should be pretty simple now that we have our mass of the meter stick. So let me put this over here. We know that the mass of the meter stick is 4 kilograms from the previous slide. So now let's figure this out and get our sum of forces. And in order to be in static equilibrium again, the sum of all forces must be equal to 0. So let's see what we're going to have here, just based on our free body diagram and where the forces are pointing. What is the sign conventions of these forces? So it looks like we have two downward forces, two forces of gravity based on the rock and the meter stick, and upward force of the fulcrum on the meter stick. So we should have two negative forces, so I'll put F as positive here, so sum of all forces. And this should be in the y direction equals MAY. We know if we're in static equilibrium, we're not moving, so that's 0. So the sum of all forces in the y direction is equal to 0. So let's look at our free body diagram again, or just the diagram. We have a force going upwards. We'll call that a positive force, F. And we have two forces of gravity. So we have minus FGR, and we have minus FG meter stick. And this is all going to be equal to 0. All right, so let's plug in the values that we got here for the force of gravity. Actually, let's do the algebra here real quick. So we should add these both to the other side, and we should have the force pushing upwards is equal to these two forces of gravity going downwards. So that will cancel, this will cancel. We're going to have F is equal to the force of gravity on the rock plus the force of gravity on the meter stick. All right, so let's plug in our values here. So we have F equals, we know Fg is mg, and that's of the rock. And then we have Fg is going to be mg. So we have mg, and that is of the meter stick. All right, so now let's plug in our numbers. We have the force going upwards here. This is what we're looking for, equal to the mass of the rock. The mass of the rock here is 6 kilograms. That is times g, which is 9.8 meters per second squared. Plus the mass of the meter stick, which we just found, and that is 4 kilograms, times the acceleration due to gravity on that as well, so 9.8 meters per second squared. Again, in the previous part here, the R and the M are just subscripts to show that that's the force of gravity on the rock and the force of gravity on the meter stick. So let's now plug this into our calculator. So we should get our force here. So F is equal to, we have 6 kilograms times 9.8. That is going to be 58.8 newtons. Plus 4 times 9.8. That is going to be 39.2 newtons. And then all you gotta do is add those two values together, and you should end up with your force upwards. And the force upwards is going to be, this is not working. The force upwards, I'll put it over here. The force upwards is going to be 98 newtons. So that 98 newtons should balance us out and keep the entire system in static equilibrium, along with the sum of all torques there in the previous part of the question. So let's move into example number 2. All right, so example number 2. A plate revolves around its center on a spindle with an angular velocity omega, which is equal to 2.0 radians per second. What is the linear velocity of a point that is 0.032 meters from the axis of rotation? This one's a pretty simple question here. What we have here is my angular velocity, so let's write out everything I have. My angular velocity is 2 radians per second. What I also have here is a radius of 0.032 meters. And I'm trying to find my linear velocity. So how do I go from angular velocity into linear velocity? This is a quick calculation here. The equation is not in the AP Physics 1 reference table, so you have to memorize it. But in order to go from any angular quantity into a translational or a linear quantity, whether it's displacement, angular acceleration, or angular velocity, all you're going to do when you have all of this is just multiply it by the radius, or how far you are from the axis of rotation. So the equation is just this. It's the translational velocity is equal to the angular velocity times the distance from the axis of rotation, or my radius. So we have here v is equal to, I have the angular velocity that is 2 radians per second, and I have my distance from the axis of rotation as 0.032 meters. All I'm going to do is multiply these two numbers together, and I should end up with my answer. So 2 times 0.032, and that is going to be 0.064, and now it's going to be back to meters per second. So that's your final answer. Let's move into our next example. All right, so moving into number 3 here. We have a long roller in the form of a solid uniform cylinder. It's being pulled horizontally by a horizontal force B applied to an axle through the center of the roller. The roller's radius is 0.59 meters, and it has a mass of 48 kilograms. What magnitude B of the force is required to produce an acceleration A, 4.2 meters per second squared, of the center of mass of the roller if it rolls without slipping? So the first thing I see here that jumps out at me is that I have a long roller. It is a solid uniform cylinder. All right, so it's giving me this shape. It's giving me, I have a radius of the roller. I have the mass of the roller, the acceleration of the roller, and it's saying that it is not slipping. All right, so the first thing here, not slipping, means that the roller is actually able to rotate. What we usually deal with throughout the entire year is non-rotating objects. We usually deal with like boxes going down inclines, boxes sliding, and things like that. Now we're going to have this wheel, and it is rotating and moving while it is doing that. So that's what that means. And in order to actually have this rotation happen, if I am going along a surface, like a lawn here with a lawn roller, there has to be some kind of friction in the opposite direction, creating the torque that then creates this rotation. So we're going to deal with that. What we also have here is a solid uniform cylinder, and I've given the moment of inertia for that here on the page as well, so that is going to be important. So this type of question is a combination of both linear dynamics and rotational dynamics. We're going to use both in order to actually figure out what we are trying to find here, which is the applied force on the roller. All right, so let's start off here with some linear dynamics, and then we're going to get into rotational dynamics. So here on the right side, we're going to work with the linear dynamics. So in linear dynamics, we have the sum of all forces equals mass times acceleration. And then in rotational dynamics, we have the sum of all torques equals the moment of inertia times the angular acceleration. Alright, so let's start off with our linear stuff first. What forces do we have? We're going to make a little free body diagram. I'm going to figure out what forces we have and see what we can do from here. So what we have here in our free body diagram, going from the center of mass, we have a force of gravity going downwards. We have this applied force B. Again, or if this to actually have any rotation, we must have a force of friction creating that torque in order to actually have the object rotate. And of course, we have a normal force going upwards. All right, so since we are accelerating in the horizontal direction, let's look at our horizontal forces and create sum of forces for that. So we have a force B. I'm going to call that just FB because it is an applied force, and that is in the positive right direction. So we have F subscript B. In the opposite direction, we have the frictional force, and then that is equal to mass times acceleration. We have the acceleration here. We have the mass, but we are missing both forces. All right, so how are we going to find at least one of these forces first? Because the ultimate goal is to find the horizontal force B, but we don't have the frictional force. So how are we going to find this frictional force here in order to then help us find the applied force FB or just B? This is where we're going to use rotational dynamics. So what is actually creating this rotation? It is that force of friction. So that is actually creating a torque on the cylinder here. And that torque is going to be an applied force 90 degrees, so we're not going to worry about an angle here. So what I have here for my torque, here I'm going to plug in for that force, or what the torque is, it is the force of friction times the radius, or the distance from the axis of rotation. On the other side here, I have the moment of inertia. That is given to me as 1/2 mr squared, and I have alpha. I don't have alpha, but we talked about this in a prior question. How do we go, in order to not have now more than one unknown here, or another unknown here, how are we going to use alpha with what we know in order to actually find our answer? What we could do with alpha is make it into translational or linear coordinates. And we can do that just like we did example number 2, where we went from angular velocity into translational or linear velocity. We can do that the opposite way and go from angular acceleration into linear acceleration. So angular acceleration here, linear acceleration, A, is equal to angular acceleration times the radius. So a quick little algebra here, this will get crossed out, and alpha is equal to A over R. So I can actually plug this in here, and we have that our acceleration, which we have the linear acceleration, is going to be over my radius. So that's going to be the same thing as my angular acceleration. So something else I can do here that'll make my life a little bit easier. If you look at this, we have the force of friction times the radius is equal to 1/2 mr squared times the acceleration over the radius again. If I do something real quick here, I can divide out the radius from this side. probably left with FF is equal to 1/2 mr squared over ar squared. Alright, so that can actually help us to now cancel out the radius or the distance from the center of, or the axis of rotation, my bad. So now this r can be canceled out because we have the same amount of them, and I'm going to be left with my force of friction is equal to 1/2 ma. So now I have what I need in order to find my applied force. I have here that FB minus 1/2 ma is equal to mass times acceleration. So now let's plug in everything that we know and we can find our applied force. Let's do a little quick algebra right here. So we're going to add this over to the other side. That will cancel over here. What I'm going to be left with on this side of the equation is essentially F subscript B is equal to ma plus 1/2 ma. Alright, so now let's plug in what we have here and we can find the applied force B. So we have FB, we're going to bring this down here. Same thing as our applied force B up there that we're talking about. We have the mass of the cylinder that is going to be 48 kilograms times my acceleration. So that is 4.2 meters per second squared. Plus now just 1/2 of that, so 1/2 of 48 kilograms times 4.2 meters per second squared. Alright, so let's plug this into our calculator and we should end up then with our applied force here. So 48 times 4.2, that's going to be equal to, so we have FB, So 48 times 4.2 meters per second squared, that is going to be 201.6 newtons plus just 1/2 of that. So you have 48 times 4.2 divided by 2, that is going to be 100.8 newtons. So now I'm going to have my applied force here, FB, add those two numbers together, and we should end up with our answer here of 302.4 newtons. So that is equal to B as is stated up there in the actual question. So we have our applied force is 302 newtons. This is a combination of both linear dynamics and rotational dynamics. So let's move in to our next example. So the next example here, we have the flywheel of an engine has a moment of inertia of 1.6 kilograms times meters squared about its rotation axis. That means flywheel, it's just a wheel for all intents and purposes. So it is something that is rotating. What constant torque is required to bring it to an angular speed of 400 revolutions per minute in 8 seconds, starting from rest? So what do I have here in this question? I have a moment of inertia, so let's write this all down. So I have I, and that is equal to 1.6 kilograms times meters squared. What else do I have here? I have what constant torque? That means I'm looking for torque. So let's put this here as my question mark. Is being required to bring it to a angular speed of 400 revs per minute. So we're going to write this down, and this is my final angular speed. 400 revs per minute, and we're going to deal with that in a second. It says 8 seconds, so we have a time here of 8 seconds. And it says we are starting from rest, so our initial angular velocity is 0 radians per second. Alright, so you notice here that I wrote down my initial angular velocity in radians per second, we are given the final angular speed in revolutions per minute. So what I'm going to have to do here is somehow move from revolutions per minute into radians per second. So this is a fairly simple conversion, just like any conversion that we've done before. All I'm going to do here is take revolutions per minute here and make it into radians per second. There's actually one last thing we are missing here as well. We are missing the angular acceleration, and we're going to end up with that in a second. So in order to actually figure out the torque here, we're going to find the angular acceleration, and that is going to be found through angular kinematics. So let's put our angular acceleration, and that is a question mark for the moment. All right, so let's go from revolutions per minute into radians per second. So just like any other conversion, we start off like this: 400 revs per 1 minute. So let's see here. In one revolution, how many radians are there? We know this in one whole revolution. In radians, that is 2 pi. So that stays on top, and we say that one revolution is on the bottom. So revolutions cancel out. And then to go from minutes into seconds, we should know this already. We have minutes here. 1 minute goes on top in order to cancel this out. And then in 1 minute, we know that 60 seconds is that. So minutes cancel. And I then should end up having my conversion here. Make sure when you do a 2 pi in the calculator, you put either parentheses about it, or you just do 2 pi by itself and then multiply the numbers here. So you have 2 pi times 400, and it ends up being divided by 60, and we're going to end up with our final angular velocity, and this is going to end up being 41.89 radians per second. All right, so now we finally have our proper final angular velocity here. All right, so now from here we need to find our acceleration, because we know when we have torque and we have a moment of inertia, the sum of all torques equals moment of inertia times angular acceleration. In order to find that, we're going to do that using angular kinematics first, because we have enough to find the acceleration that way, and then plug it back into the torque equation. The sum of torque equation equals moment of inertia times angular acceleration. So what am I going to use the equation, what angular kinematics equation am I going to end up using here? I have an initial velocity, I have a final velocity, I have a time, and I'm looking for acceleration. So that equation is going to be our final angular velocity equation. Angular velocity, the final angular velocity, is equal to the initial angular velocity plus angular acceleration times time. So let's plug in everything we have here. We have 41.89, and that is radians per second, is equal to 0 radians per second. Oops, let me fix that. Plus alpha, which we are looking for, times the time, which we have as 8 seconds. So we have 0 here. This doesn't really matter. What we're going to do here, we have 41.89 is equal to alpha times time. In order to get alpha by itself, it's being multiplied by time. We divide out 8 seconds from both sides of the equation, and we should end up then with our angular acceleration. So let's plug this into our calculator real quick. 41.89 divided by 8 is going to be 5.24, and that is radians per second squared is equal to alpha. All right, so our last part here, we need to find the torque on this. So our equation for torque, like making it like Newton's second law, we have sum of all torques is equal to the moment of inertia times alpha, we are given the moment of inertia in this question, and we just found the angular acceleration. So all we have to do now is just multiply these two numbers together. So the sum of all torques in this question is equal to the moment of inertia, which is 1.6 kilograms times meters squared, multiplied by the angular acceleration, which is 5.24, and that is radians per second squared. So let's multiply these two numbers together, and we're going to end up with the torque required to bring this to this speed. So 1.6 kilograms times meters squared multiplied by 5.24 radians per second squared, and we're going to end up with an answer here of 8.38 newtons times meters. So the sum of all torques here, or a net torque, is going to be 8.38 newtons times meters. And that is our final answer. So let's move into question number 5. Let's move on to example 5 here. I have a square metal plate that is 0.18 meters on each side. It's pivoted about an axis through point O at its center and perpendicular to the plate. See the figure below. So we have the figure here, and it shows that square plate and how it is going to end up rotating. Calculate the net torque about this axis due to the three forces shown in the figure if the magnitudes of the forces are F1 is equal to 17 newtons, F2 is equal to 27 newtons, and F3 is equal to 13 newtons. The plate and all the forces are in the plane of the page. Alright, so what I have here looking at my diagram, and when I ask for net torque, this just means we are looking for the sum of all torques. So the sum of all torques, and we're going to set this up. So let's first look at all our forces. So let's start off with F1. So look at F1 here. This is the force here, and this is the axis of rotation. So if this force is going downwards, it is going to spin the plate in that direction. That direction is going to end up being clockwise, and we know based on our sign conventions that clockwise is a negative torque. So our torque for F1 is going to be negative, and we're going to say that that is torque 1. So now looking at torque 2 created by force 2. So let's look at this one right here. Again, our axis of rotation is in the middle. If we were to spin the plate based on that force, it is going to spin in the counterclockwise direction. So that means we are going to have now a positive torque. Again, clockwise is negative, counterclockwise is positive. So let's write this out here. Our torque tau 2 is going to be positive. And then finally, looking at the force F3 here, this one is at an angle. We have it over here. And that one is also going to be rotating my plate. If I were to push that force there, it is going to also be in the counterclockwise direction. So that means we have a positive torque for F3, so plus tau 3. All right, so now our next step in this is being able to find the distances of these forces from the center of, or the axis of rotation. So axis of rotation, again, is O here in the middle. What I have here is a force at the points here of my square. So from the center, we have this, and we have this here, and we also have this here. So there's two ways to go about actually finding this. I'm going to do it the, I guess, longer way because we have 0.18 meters for each side of the square. So then we can use that based on what we know about squares. Half the square here is going to be a triangle. So we can use Pythagorean in theorem to then find the length of the diagonal here, and then half of that will be the distance of the force from the axis of rotation. So let's do this real quick. Obviously a squared plus b squared equals c squared. We have a squared, that is 0.18. I'm not going to plug in units here, so 0.18 squared plus 0.18 squared equals c squared. Let's plug this into our calculator. So 0.18 raised to the second plus, so 0.18 raised to the second. Oops. That is going to give me a total value here when I add these two numbers together of 0.0648 is equal to c squared. Take the square root of both sides because that's how we get c by itself. And I'm going to end up with my answer here. The total distance, the total diagonal is 0.25 meters is equal to c. And then if I divide 0.25 by 2 to get my distance there, I get 0.125. I'm going to round it off as just 0.3. So I'm going to show this on the diagram here. The distance here is going to be 0.13 meters. So that's just the 0.25 divided by 2 again. That's where that 0.13 comes from. Ends up being 0.125, but I'll just round off to 0.13 meters. Alright, so now what is the sum of torques and what is the equation for torque? We know that that is Fr sine theta, and since we have one at an angle here, that is going to become a little bit more important. Again, let's look at our first two forces and see if we even need to plug in sine theta here. So I have the sum of all torques that is equal to, both F1 and F2 look like they are perpendicular to my plate here. So I have here minus F1 times R plus F2 again, and we don't need sine theta. Again, sine of 90 is 1. So we don't need to plug this in for forces that are perpendicular to whatever I am rotating. So that's the same exact deal for F2. We have F subscript 2 times the axis of rotation, then plus tau 3 here, and that is going to be F3 times the axis of rotation times sine theta. Because now this is at a 45-degree angle, so we have to actually worry about that angle there. Alright, so now let's just plug in what we have here, and we can figure out the sum of all torques. So the sum of all torques is equal to negative here, because that is a negative torque. Our first force is 17 newtons. That is multiplied by the distance from the axis of rotation, which is 0.13 meters, plus F2. F2 is going to be 27 newtons, times R, which again is 0.13 meters, plus F3 here. F3 is 13 newtons, times again R is 0.13 meters, but now we have sine here, and it says this angle is 45 degrees, so sine of 45 degrees. Alright, so now you're just going to plug all this into your calculator, and you're going to end up with your answer. So we have here 17 times 0.13, and that is 2.21, so this is negative 2.21, and that is newtons times meters, plus 27 times 0.13, that is going to be 3.51, and that is newtons times meters, and then plus here my final one here, 13 newtons times 0.13, and then multiplied by sine of 45. We're going to multiply these two numbers together, and we're going to end up with our torque there as 1.195, so that's going to be 1.2 newtons times meters. Alright, so now just add all these together. That's what the sum of all torques means. So add all these values together. So negative 2.21 plus 3.51 plus 1.2 newtons times meters, my bad, is going to all be now 2.5 newtons times meters, and that is our final answer. That is the sum of all torques, or the net torque. Alright, so let's move into example number 6. Alright, so example number 6, we have a disk is free to rotate about its axis perpendicular to the disk and passing through its center. If the disk starts from rest and accelerates uniformly at a rate of 5 radians per second squared for 4 seconds, what is the angular displacement during this time? So with any question like this, what I'm going to do is write out what I'm given in the question. So I recognize my kinematic quantities. There I have an acceleration, I have time, it says I'm starting from rest. So let's write all those things out and figure out then what kinematic equation I'm going to use for this angular kinematics. So we have here that it says that the disk starts from rest. So I have here omega naught is equal to 0 radians per second. I have also the acceleration. So I have acceleration is going to be 5 radians per second squared. I then also have my time, that is 4 seconds. And I'm trying to find angular displacement, so that is change in theta. So what equation is going to use? My initial velocity, my angular acceleration, my time, and my change in displacement there, or my displacement. And that equation is going to be my displacement equation. So change in position is going to be equal to the initial angular velocity times time plus 1/2 alpha times t squared. So what I have here again, I have initial velocity of 0, so this whole part's going to go away. I'm looking for my displacement. Change in theta is equal to 1/2 the acceleration, which is 5 radians per second squared, times the time squared there, so that's 4 seconds raised to the second power. Alright, so now you're going to plug this into your calculator here. So the change in theta is equal to 1/2 5 radians per second squared. So 5 radians per second squared times 4 raised to the second power. So that's 16 times 5 divided by 2. And you're going to end up with your final answer. So change in displacement is equal to 40 radians. And you can keep it as radians because it's not asking you for how many revolutions or anything. This is the displacement that we are looking for here. And this is our final answer. So let's move into our final example. So our final example here, we have an inclined plane makes an angle of theta with the horizontal as shown below. A solid sphere of radius r and mass m is initially at rest in the position shown, such that at the lowest point of the sphere is a vertical height h above the base of the plane. The sphere is released and rolls down the plane without slipping. The moment of inertia of the sphere about its axis to its center is 2/5 mr squared. So this is a sphere and not a cylinder, so it has a different moment of inertia. Express your answers in terms of big M, big R, h, g, and theta. So determine the following for the sphere where it is on the plane. So we're going to break this up into 2 slides as well because it becomes a little bit much for one slide. I don't want to squeeze everything into one here. So we have 2 parts here. We have find the linear acceleration, so essentially derive an expression for the linear acceleration, and then figure out what the magnitude of the frictional force is based on the expression for linear acceleration. Alright, so this is very much like the question from earlier. It is now just on an inclined plane, a little bit of a different moment of inertia. So instead of me pulling this object, so let me write out my forces here. So I don't have to be precise here with my free body diagram because it's not asking me for a free body diagram. So I'm going to show the components here as well. So I have here FG. I have Fn going upwards. Alright, in order for this object to actually roll without slipping, again, I need some kind of force of friction opposing it in order for this object to actually rotate. And then for FG, what is actually bringing this object down the plane? It is the force of gravity, but what specific force of gravity? And we have to go into our components for this. So inclined planes, we have straight downwards, we have a perpendicular component. Along the plane, we have a parallel component, and that is FG parallel. All right, this angle here is the same thing as the angle of FG between FG and the perpendicular component. Opposite of that is FG parallel, is the same thing if we bring it up here. This is also FG parallel. That's just being moved upwards. Or the arrows are being moved upwards. So it's the same exact thing here, opposite of that angle. Opposite over hypotenuse is sine. So FG parallel, FG is mg. We multiply this by sine theta. So let's create first the sum of forces based off of this to find our linear acceleration. And we'll also have to bring in, again, since it is rotating, the sum of all torques as well. All right, so let's see here. So with linear acceleration, we have the sum of all forces. And this is going to be parallel along the plane, is mass times acceleration parallel. All right, so going down the plane, we'll call that positive right now. The force that is bringing me down this plane is FG parallel. Opposing this is the force of friction, so we have FF is equal to the mass of the object times acceleration here. All right, so yet again, what is this FG parallel? We have an angle here. This is an angle between the force of gravity and the perpendicular component of the force of gravity. And this angle is the same angle as the one on the incline here. So since we have this angle here, opposite of that is FG parallel. This is going to mean, we know that FG here is mg. And then this parallel component here is going to make this sine theta because of where my angle is. This is minus FF is equal to MA. All right, so based on this, I'm trying to find acceleration. I don't have enough right now to do that because I don't have the force of friction. So I can't just call it a day and divide out m and say that I have the acceleration and it's mg sine theta minus ff over m. What I'm going to have to do here is also bring in my rotational dynamics, and that is the sum of all torques. So the sum of all torques is equal to mass, which is the moment of inertia here, and the angular acceleration. So we don't have our angular acceleration. So once again, just like in the earlier problem, what we're going to do with this angular acceleration is make it into translational or linear, into a linear situation. So we have here that acceleration is equal to, if you want to go to a linear from an angular, all you're going to do is multiply the angular by the distance from the axis of rotation. So to have this angular quantity and make it into linear, then we're just going to divide out the distance from the axis of rotation. So we have the angular acceleration is equal to acceleration over that distance. And so what I have here, I have the sum of all torques. That is equal to a moment of inertia, which we were given in the problem, and this is for a sphere. So it is 2/5 the mass times the distance from the center of, or the axis of rotation, squared, and now times a over r. I'm gonna make this big R for now. So then what is torque here? So what is actually causing this object to rotate is the force of friction. Without the force of friction, this object is not going to end up rotating. It's just going to slip down the inclined plane. So that's the only force that is creating this torque. So when I have torque here, the sum of all torques, I have again now the force of friction that is times this big R here. And again, this force is going to be perpendicular to our sphere, so we're not going to worry about sine theta because sine of 90 is 1. So now this is equal to 2/5 the mass times r squared times a over r. So our last thing here, what I'm going to do here, I want to get rid of this r, and I can easily. So if I divide out r over here, I should end up with ff is equal to 2/5 m r squared over a r squared. This all cancels. So the force of friction is equal to 2/5 the mass of the object times my linear acceleration. So now we can find linear acceleration. We go plug this back into the equation. We have mg sine theta is minus 2/5 ma is equal to mass times acceleration. So real quick here, in order to get this all done here, I have my mass is actually going to cancel out as well since I have the same mass all the way throughout. So I should be left with here g sine theta minus 2/5 my acceleration is equal to acceleration. What I'm going to do here, just to make my life a little bit easier because we're working with fractions, I have here 2/5 on this side. This is essentially 1 times acceleration. So I have here g sine theta minus 2/5 my acceleration is equal to 5 over 5 times my acceleration. Let's move this all over here right now. Oops. The reason why I changed this to 5 over 5, it's easier to work with now when I'm working with fractions, because I'm going to have to add up these a's in a second, and I essentially had 1 times a, so 5 over 5 is still 1. So I have g sine theta here. In order to get this a by itself, by first step, move this theta aside, so 2/5 a, that cancels, so I have g sine theta. On the other side, I have plus 2/5 a, so I should be having on this side 5 over 5, 5 plus 2 is 7 over 5 times my acceleration. Now in order to get acceleration by itself, I divide this out from both sides, so it cancels over here, and then I flip my fraction, so I should be left with 5 times g sine theta over 7 is equal to my acceleration. So we're going to use this value here in the next part of the question to actually get our value for the force of friction, because we found the force of friction here already. Now we just have to plug in this acceleration in order to do this. So let's move on to part B. Let's do a refresh on what we had there in part A. So we have here that we found that the sum of all torques, we know that is the moment of inertia times the angular acceleration. What we figured out was that torque is being created by the force of friction. So we have the force of friction times the distance from the axis of rotation. Again, sine theta is not going to matter because that force is perpendicular to our sphere. So we don't have to deal with that there because sine of 90 is 1. That is equal to the moment of inertia, which we have here given to us. That is 2/5 times big M r squared. And then we figured out that the angular acceleration, we can change that into translational, and that is a over r. So let me go back and fix this r here. All right. So from there, we figured out then we could just divide out r from both sides, I have the force of friction. And my R is going to end up canceling out. So 2/5 m times R squared here over A R squared. So this is going to end up canceling out. So my force of friction, we figured out, is 2/5 m A. And then we also figured out what A was equal to. A was equal to 5 times G sine theta over 7. So now what we could do is plug in this acceleration into what we figured out the force of friction is, and we have an expression for the frictional force, or our magnitude for the frictional force. So let's plug this in over here. We have that FF is equal to 2/5 times m. Acceleration was essentially 5 over 7 times g sine theta. So what we're going to do here now is look at my fractions. What I have here is 2 times 5 over 7 times 5, or even simpler, I have a 5 on the top and a 5 on the bottom. The 5s can cancel, so I'll have 2 over 7. So I have here the force of friction is going to be 2 over 7, or if I do this all the way out here, so we have 2 times big M times G times sine theta all over 7. So again, we were just taking the acceleration we got in part A. We pretty much figured out what the force of friction was in part A or part 1 as well. And then we just got to plug in that acceleration to our expression for the force of friction, and we have a full answer here. 2 over 7 times mg sine theta, or 2 times mg sine theta over 7. All right, so this is our last question. So I hope this was a helpful explanation, and see you guys in class.